So isotropic, you know, right? What do we call isotropy?
So it's like same stream in all directions.
Yeah, yeah. So it's yeah, okay. So the basic definition of isotropy is the constitutive relation won't change in any direction. Or not that actually, the properties actually. So the properties do not depend on any direction. So it's isotropic material is the material where we require the least number of parameters.
I think it's like if you take a body.
Yeah, yeah, yeah.
And if you do like this.
Okay.
Like this. And if you
Uh
do
-huh.
like this, the
Yeah.
strain would be same.
Right. Yeah. Yeah. That's true. Actually, the thing is what you said, right? Dinesh, that is actually a definition of objectivity. Yeah.
Okay.
Actually, there is a very subtle difference. So I'll just show you that relation actually, like the.
True.
So for what you call objectivity. I'll just remove this. No need. We are not solving exam. So objectivity, what we see is we have some material, it gets deformed, and then you apply some rigid body motion by which the what you call the shape and the same shape remains the same. So it's like this is our what we call psi. X vector psi is the mapping, and this is like rigid body motion, or what we call as superimposed rigid body motion. So we had a point X vector material point, isn't it? And then this it would deform to some X vector, and then it deformed the same became X vector star or X vector tilde based on, yeah. So this is what is objectivity in the sense that objectivity, I mean, the thing is in objectivity after SRBM, there are certain relations which has to be satisfied by a scalar, by a vector, by 2-point tensor, by we saw right certain relations. So that is only if the relations are satisfied, which means the rotation only rotates. So it's like you are just transforming, say if you're say you are transforming a vector in after deformation to something after doing rigid body motion. So it's just like, so if there is some rotation, then the vector will just rotate. So objectivity simply means that it satisfies the standard transformation laws of a vector of a matrix or something like that. So say if you have a vector P, right? And then you apply what you call rigid body motion. So you know that in rigid body motion it consists of two parts.
Yes,
yeah, two parts: rotation and translation. Now you know there is a property of vector, right? That vector is invariant under what? Translation. Sorry, it's translation actually.
Invariant matlab?
Means even if you translate it, vector always remains the same.
I mean, even if you rotate it also is same.
No, the thing is after rotating you are actually changing. So given a coordinate frame, right? So yeah, you must also vector, no. Yeah, you must always, yeah, the thing is vector, right? Vector is always free floating. So if the vector is like this, if you translate it anywhere, it will always remain the same.
No, I think I'm sorry, I have to disagree.
Okay, I'll just tell you why what vector.
No, I understood. Understood the point. Yeah. No, but the point I'm trying to say is, so what you said is if you just translate it. So what you're saying is, say you have initial vector A, let's write A.
Yeah. Yes. Yeah.
Then say that you add vector B to it.
Yes.
Right? Just translate it.
Yes.
Then what you're saying is A plus B is a new vector C, which is same. So actually,
I must tell you, actually, when you talk about vector, right? So you must always see vector as which has certain head and certain tail.
Okay.
So no matter where you translate, right? So think of vector as some I mean, I don't know, we should not go into that aspect, but think of something like what do you call something like say direction and magnitude. Think of something like that.
No,
Yeah,
I wouldn't have said
yeah,
this to somebody else,
yeah,
but you know a lot of stuff, so I'm telling it to you. As in,
yeah.
but the way
Huh.
when you say vector, I
Yeah,
normally
yeah.
say a vector because you
Yes.
know, no, we have three principles.
Yeah, actually, I'll tell you actually something I
So
need
the
to tell
vector
you.
principles are what? It should be a set. Any two
So
elements of the set has to be equal. Then see, you know,
ex
no, I'm talking
ex
about that like
yeah,
two
let
branches.
me clarify your point. I think you now you will find it. I mean, agree actually.
Because this point and direction is a very bad representation of vector.
Yeah,
Nobody should
yeah,
ever teach
yeah.
vectors
See,
like this. It's
exactly.
bad.
See what we are doing is, see you have C vector. You know, even the endpoints of a vector have certain things is like Poisson vector, right? From some origin, isn't it? Isn't it like this? So this is C and this is D, right? Now I must actually, the thing is to clarify, right, what I mean here. So like C and D, fine. These are the endpoints of a vector. So the thing is like vector is just the relative, the head minus tail of that of something, isn't it?
ऐसा नहीं
Yeah.
ऐसा बोल सकते हैं but point is whenever we say like this no then we are
Yeah.
running ourselves into big trouble. I think we should
No,
always say
that's
it
true.
in
That's true.
terms of
That's true. That's
vector
true.
is like we have no that rules should be
हाँ हाँ.
set मैंने दो ऐड किया तो सिर्फ वो should
Yeah.
come the same thing. That is how
Right.
we should represent vector.
Yeah.
Because see
हाँ
now
हाँ.
I can say something and it's very difficult for us to because for you to explain like you have to hold your ground. But anyways,
Right.
yeah, please continue. C and
Yeah.
D.
So what I was saying is, so see D vector and C vector are like the endpoints, right, of this vector.
Yeah, correct.
So like, I mean, it's just like vector, it's just like some relative vector, isn't it? So when we translate, when we do transformation, you recall what we did in SRBM. In SRBM, we actually transform the points, isn't it? So we are transforming the material. So say we have X and you have Y.
Okay.
So it becomes X tilde and Y tilde, right? And both are actually undergoing. So Y tilde is equal to Q Y plus some constant C, and X tilde is equal to Q X plus some constant C, because it has to be the same translation, isn't it? Now you see something that when you subtract, then you get this material element, or what you call as the material vector, or material fiber. I mean fiber material vector. That's how you call it, right? This is the fiber vector actually. So when you do subtraction, that is when you get this fiber vector. I think I should have been actually. I'm really sorry for using the bad words, right? Like this is how. So it's always fiber vectors that we are working with. And the thing is, it's we cannot say about this Poisson vector, because the thing is, if you have the same what you call the, if the coordinate axes are fixed, then if you shift, obviously it's going to change. The Poisson vectors of the points are going to change. So like D will become D prime, and the C will become C prime. However, I'll just use E actually, not too confused. OK. However, when you look at and then both have translated by some C vector. Now, however, D prime minus E prime is still, so it's like D plus C minus E plus C, right? So it's like under pure translation. So any what you call vector which are connecting, which are, I mean, at any material fiber vectors, they will always remain the same. You see, right? This is the same as D minus C under pure translation. So it's only after when we do, so it's only the rotation which affects them. You see, right, on the right hand side here, I'm doing that rotation part. So it's like X minus Y is equal to CC cancels out. You just have Q X minus Y.
So what you're saying is after rotation, but still
Only rotation vector, oh, sorry, rotation only changes the material fiber vector. Pure translation vector doesn't change the material fiber vector. So that how I should frame is that the relative,
changes are it's just same no.
no, the thing is it gets rotated, right? So x minus y is different from x tilde minus y tilde, right? Isn't it? Because q actually make, I mean, q is a transformation over x minus y. So q acts over x and y to give x tilde minus y tilde.
If you look at the magnitude stays same, no?
Yeah, the thing is to be invariant, both things should remain the same. It's a unit vector. It's what we call, it's a unit vector as well as the magnitude. Both should remain the same to be invariant.
I think this, and okay, understood. Of course, I agree with you. Completely
Yeah,
agree with you.
But yeah, before actually I was wrong. I'm really sorry. But the thing is, it's not vector. It's only relative vector which remains the same after translation. Yeah. And
yes,
so that is where object.
Maybe
Yes.
Maybe I will just look into this writing now.
Yeah.
Like invariance in abstract notation. When can we say a vector is invariant? Like this is okay. I agree with this. I mean, this I understood, but like just like what happened was I was defining. So my Professor Prabhu.
Yeah.
Professor Prabhu, while he was teaching one course, he asked this question: how can you define a vector? And everybody says it has a magnitude and direction.
Yeah. Actually, that I learned during my masters. Even bachelor's, I had was introduced, but I could not understand. In only during self-learning that I did, that I understood. Okay, so it's a mathematical object which satisfies certain relations.
Exactly. So,
Then it's a vector.
So someone says magnitude and direction. Then what Prabhu said is, okay, say that I have a 5 kg bag rice, rice bag, pointing in northwest direction. Like I put it from 2 kilometers from here or 20 meters from here. Do you think this will be a vector? Because it has magnitude and it has direction. You understand? Say that so you are in IIC, you have some weight. I will say you are vector. It's not how it works.
No.
It has to satisfy some rules. So
yeah, there are. Yeah.
So then after reading some that abstract maths like real linear algebra, then in linear algebra they'll say, but if you go deep only you will understand. It's not. It won't be.
Yeah, exactly. The thing is, vector spaces are topological spaces fundamentally. So that's how it goes.
Yeah, so it's like you have big spaces, then go down.
Yeah.
And there you have this.
Yeah. Exactly. What we call vectors are finite dimensional vector spaces. What we call vectors.
It has some name also, no? Like finite dimensional vector space has a specific name.
Rn space. Rn space. Usually that's how we say that.
There are a few spaces which are finite dimensional and which where norm exists, where norm doesn't exist.
Okay, that is Hilbert space.
Hilbert, then you have like norm, then you have square root.
Yeah, so when a so when you have norm defined over a vector space, then you call it a.
Oh, you're stuck.
Is it fine now? Just yeah.
Okay, it's again gone.
And now,
put video off. Put video off. That's the best thing.
Okay.
Video off. Just video. We will put video.
Sure. Yeah. So when you have this what you call inner product defined over that, right? Inner product defined over a vector space.
Yeah, exactly.
Then you call Banach space. Yeah.
Yeah, exactly.
And when you have what we call inner product defined over the vector space, then it belongs to it's called as pre-Hilbert space. And if the Hilbert space happens to be complete in the sense that all Cauchy sequence in that Hilbert space converge, then it is known as a Hilbert space. So there are two terms. So pre-Hilbert space is a vector space over which you can define inner product, and then when you have what you call and then when you have when all the sequences in that Hilbert space converge in the sense that even its limit exists in that space, then it is known as Hilbert space. It's just all those mind-boggling definitions.
Yeah.
And the thing is what we call norm, right? what we usually call norm, isn't it, Dinesh? The one that we usually tend to use. Those are, I mean, more precisely known as induced norms.
Okay. Yeah,
Yeah,
that's true.
yeah. The reason is
So
because we use
I think the norm automatically exists. That's what induced norm is, right? Yeah.
no, because no, it's not that actually. Induced norm is because we use inner product to define a norm.
Okay, that's what. So it's like automatically never exists. So your norm automatically exists because you just take square root of it.
Yeah. So we define norms using inner product. So that's what I mean here. Yeah. So because there are infinite norms, and inner product is one particular. I mean, a very standard definition of inner product. However, there are infinite norms. So the one we use is induced norm because the thing is we use inner product to define that norm. We just take square root of that inner product. So you have vector u, then so u dot u or u comma u, and then square root, positive square root of that is taken to be the norm. So these are induced norms.
But I understand the invariant you're talking about. But it is interesting. It's definitely interesting to see how this invariance would propagate. Or,
Yeah.
Describe
Okay.
when you deal with abstract spaces such as rules.
Yeah, actually, just wonder, Dinesh. I mean, how would a vector remain invariant? The thing is, for a vector to remain invariant, right?
I mean, so it has to be same.
Yeah, direction and what do you call not direction. I mean, to be more accurate, we would call that the norm and the unit vector should remain the same.
Direction is unit vector. Yeah.
Yeah. Or otherwise, we can say that if it maintains the same what you call no, that would not be actually convincing, yes, because we can have multiple inner product with a second vector, right? So the thing is, invariance of a vector is just that what you call under rigid body motion. Invariance of a vector means that it should remain at the same place. That's what we saw, right? That's what we saw here, right? Because when we just translate, then it becomes d plus.
If the what if the dimension is like infinite dimensional vector? Okay, then we will get into one more trouble, right? So it's
the thing is
very funny thing.
Yeah, because we are adding something to it, right? So that's why actually I understood when you actually clarified, then only actually I understood, okay, what you are trying to say. So it's only the relative vector which is invariant under translation. And we have easily been able to show that d minus d. So in spatial, so if P is some vector connecting two different material points, then it's just like so the relative vector will just, so if Q is a rotation vector, then it is just like QP. So P is say a vector in material frame. So this is suppose P. It's a bit otherwise because that's how I'm doing. So so this is capital Y. So this is P actually, and this is P small. And actually, yeah, I made some mistake. This is P. This is P tilde. So and this is P tilde. So now you say, right? So what do you call it? It's only the rotation part which is affecting the. Yeah. Only rotation part of rigid body is affecting the. So this is anyway the translation. So this is anyway transformation of a vector, right? Transformation is when we are keeping the what do you call the. It's like when it's just like when you have a vector in this and defined in this coordinate system, and then you just perform some linear transformation over it, which happens to be an orthogonal tensor. So it will go somewhere here. So how will the components of that vector change within this? Or sorry, or how will the vector after transformation be? So that is what it is. So it's like the translation never affects. And for what we call purely spatial tensor, we had say sigma tilde is equal to q sigma and q tilde, right? Sorry, q transpose, isn't it?
Yeah.
This is what we learned about the objectivity. I mean, the relations, right? Now, for isotropic, there is a slight difference. Actually, there is where the key lies. So when you say that, under objectivity, say if you have a, I'll just use another under objectivity. So given, what do you call an energy functional? Given an energy functional, say W as a function of deformation gradient, and then we learned that it is also equal to W QF, or otherwise
Correct.
F tilde, F tilde, and then this is becomes QF.
Yeah.
So it means that under, from the principle of objectivity, that the energy should, even after there is what you call, even after superimpose, imposing this
Rotation.
rigid body motion, the energy should still remain the same.
Correct.
However, for isotropy, there is something else going on, and that's what we are going to talk about. So isotropy, there is, it's very tough to understand. It means even I have not understood even now. I just try to decode from the relations. So it's like, how you define isotropy? Isotropy is when you have this final configuration, right? You have such final configuration here, and this is some initial configuration from where it starts.
Okay.
Isn't? So this is like X. This is like, I'll call it X, and this is like small x here, and then is this material point, and there is some mapping defined, which is psi vector. Under isotropy, what is said that, so say if you have a fictitious, in the sense that if the initial configuration was itself, in what itself came from some other deformation, and which is just a pure rotation. So it's like pure rotation.
Okay.
Pure rotation, and so this I'll just call it capital X tilde. So even before that, the thing is, you see, right? So after rotating it, you have this this current. This is what is reference configuration, and this I'll just call it as pre-reference configuration.
Okay.
And this is our spatial configuration or current configuration.
You free at the moment? I worked out how to use the roller compactor thing.
Okay.
So what is said that there will be some net. So had this pre-reference configuration directly be taken to the spatial configuration, you understand, right? So had we been taking from here to here, so as per this rule, in both the situation, we should have the same, what you call,
Energy.
in this situation as
Energy,
in this
energy change.
Yeah, we should not
energy change, no?
Yeah. Right. So the energy should remain the same. So let's just try to understand what's going on here. So what we call, so like this is so from here to here, how will it go? Let's just try to understand. It has been a long time revising this. Let's just try to understand what's going. So so
What are you trying to do here, Krishna?
okay, the thing is, there is, I just want to understand. It has been a long time, really long time. Even maybe we could discuss this some other day also after reading.
Sure.
But the idea is we have to prove this relation.
Okay.
So this is the condition for isotropy. I just recall the, what you call, the expression, because so for objectivity it was WF is equal to W as a Q of F. So I'll just use different. I'll just use different. I'll just use different here. Yeah. This is objectivity. So this relation is always satisfied by all the constitutive relations because that is the rule.
Yeah, that's what I want to ask. Yeah.
This is not true always. So it's only for those
So what
materials
you're
in which
saying
this.
is even after rotating and
Yeah.
doing the deformations,
Yeah.
the
Yes.
net change, the new energy is equal to even
So
without rotation and changing,
yes,
giving it.
exactly.
But
It's
if
some
it is not isotropic, then of course in you, because the properties are different in different directions, the energy
right.
will not be same.
Exactly.
That's
Yeah,
what we are trying
exactly.
to say. And
That's the idea.
but that's what. So so I was getting confused with objectivity and isotropy, but I think what objectivity says is it's like objectivity means what?
After
So you first so it's like
do
so
deformations. So objectivity simply means that the constitutive relation is independent of the, or is invariant
rotation,
with respect to the, with
rotation,
respect
right?
to rigid body motion. So
Hmm.
the thing is again that we had discussed this, right? So objectivity in mathematically what we do is, let's go back here. That's a very important thing here. So you see some deformation going on in a system. You see from here, isn't it? You see these are just eyes or maybe just a person seeing from here.
Yeah.
Okay, what he sees should be the same when some other person sees from here. So both of them should see the same constitutive relation with, same relation between stress and strain.
Yeah, so I think
However,
yeah,
the thing is,
exactly. It's true.
yeah.
You're right.
So what we do is we just say that okay, this is the same as.
This
So
is
in this
not
case, what
about. So yeah, we are doing the same thing, but we are looking at different frames. So it doesn't matter. So if
exactly
we're applying the same force, but you're
right?
just dealing the science is done. Somebody is looking from Mars, somebody is
Yeah,
looking from Saturn, somebody is looking from Earth. So the
should be the
it's
same.
like it's like just if you're punching. So
Yeah.
as I'll tell you one example. So if we are, in our group, we were reading this book reading, not here
Huh,
in India, Prabhu and
huh,
everybody,
huh,
and we were discussing about vector invariance.
huh, 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 huh.
Okay, and the
Yeah.
answer I gave was, so somebody will says vector stays the same, doesn't matter from which frame you're looking at, right?
Okay.
That's what here we are looking at as well. So one good example is, say you are in a boxing match,
Huh, huh, huh.
okay, and the boxer punched you.
Yeah. Huh.
Okay, it doesn't matter what frame you look at, the punch is same, no? It's like the pain you
Exactly. Yeah.
get is that's what
Yes.
invariance is. Even
Hmm.
here, so it doesn't matter which frame you're looking at, the stress the body should, or the constitutional law should
The,
stay the same. I think
yeah, the
that's what
body should respond to the
same.
same force in the same manner.
Correct.
And this what we do is the thing is mathematically the easier thing is let's keep the what you call the coordinate frame the same. Let's rotate the body itself, or let's do some rigid body motion on the body itself. So they are like equivalent things. So in this case, what happened is reference frame is changing. Is changes and body remains at the same place. Body remains somewhere static, isn't it? In the other case, it's equivalent, not other case. It's equivalent to reference frame static and body changes, or body what you call undergoes some rigid body motion. So they are equivalent statements. No, it looks like, I mean there were, I mean people have spent really really a long time understanding this thing, that can it always be the same? The thing is, if this is not true, right? So it's like there is no meaning of doing experiments anywhere.
Correct, correct, exactly.
So experiments is based on this
No,
fact.
I think this is like obvious, no? And you say that, say that's what. So if you're getting punched, you're
Huh,
punching something, okay,
yeah.
and you say I'm in different frame now.
Huh,
The punch is should be less intense. No, like you will get brain damage or something. Like doesn't matter which frame
yes.
you're looking at.
Yeah. The
Understand?
only thing is this is only valid in classical mechanics. It's not valid in
Oh,
relativistic mechanics. Yeah, because there is
I don't know that.
time length contraction and time elongation. So there, these things do not hold anymore. Because then the thing is relative in relativistic ideas, these things are very different. Then you cannot say these things are not equivalent anymore. Like, say if the body is moving very fast and if the entire space is moving fast and the body remains the same, obviously in the second case nothing is going to happen, but in the first case he will face everything, right?
No. my friend asked me this question in masters, like interesting question. Yeah. So he said that I take in masters we are not that great. I mean,
it's all right.
So you take infinitely long rod. Okay. Then he said that I am moving the other side. Like I moved the other side. What happens to the other side? Understand the question?
Yeah, the thing is, where will you be to push it? that
would be. Say that we're at one end. We're at one end, and the tube is very long. Now I just move the body like this. How time, like then what happens to the other end? Because the waves to propagate, it will propagate at speed of sound of the rod, and so that's the answer you should give. Because if you know much physics, but usually we say that other end it will also move.
No, the thing is, if it's semi-infinite, so it's like semi-infinite, right? So it does affect it. It will be obviously different from had both sides been infinite. So because the thing is now boundary conditions.
Infinite, if it's semi-infinite, so say that the speed of sound is 2000 meters per second. Okay, if the rod is 10,000 meters per second, 10,000 meters, then it will take 5 seconds for the other end to know that someone moved it, right?
Yeah, so there will be no reflection actually.
No reflection. So it will take 10 seconds. Exactly, that's the answer.
Yeah.
And I think that's what now is like if you move it with speed of sound, what happens? That's what everything comes into picture now. Like there is other thing.
Yeah.
Quantum.
So this reflection and all only come into picture if you have finite domain.
Yes.
If there is no finite domain, there is no reflection. Yeah.
That's why even in maths, we're discussing if it is the invariant of vector, norm and everything. Once you take infinite dimensions, then norm and everything just gets complicated and just you don't know. Like
yeah.
I don't know.
Then you always have to return to what you call. We have always to come to induced norm. Yeah, it's just like you have various definitions possible. Again, the thing is we only choose the relation which gives us the. I don't know why. The thing is L2. What we do is L2 norm, right? L2 norm behaves very similar to L4 norm. So like
yes.
In infinite dimensional, but however, it's only L2 norm which we choose. So it said that it's just out of convention. There is there. I don't know what the reason is because, but the thing.
Norms. I mean, I should know about the norms because I have used them in my simulations. Just that they'll just check.
The only reason is because while defining inner product, the operations should be linear in both the arguments.
The operation should be linear in both arguments. Okay, correct.
So it's the thing that is so it's the simplest inner product that we use that actually satisfies linearity in both the arguments.
Okay.
So I mean, just as a proof, right? So you are given say U and V. There's inner product. Inner product, right? And then what we have is, and then say you take U to be alpha A plus alpha beta B. So you can see that from the principle, I mean, the way do we define linearity, right? So it should be, so this comes out to be alpha A V plus beta BV. Isn't it? Because this is how we define. So this we just define U into V into integral over some domain. And this actually comes out neatly. So had this not been this one. So say what we are discussing is say what if UV is equal to U squared V square, then it actually becomes what I was telling some L4 norm like meaning. Then in that case, this linearity won't hold anymore. So that is the reason we always take this L2 has all the properties that we need. I mean, for the definition. Yeah, that's. I have never seen this explained, but I mean, maybe this is how I mean, I think could be the reason. Like, it's linear in both the arguments, so this could be. I mean, it's of much use. It's just like why do we need orthogonal basis? Even linearly independent basis also does the same work, right? So why do we need orthogonal, right? It's just because of its special properties. Yeah.
Yeah.
It has some important properties that okay, one component doesn't affect the other component, and so that's why there's all this Gram-Schmidt process came into picture, isn't it? So this was what we are talking about isotropy. Actually, we need to learn the mathematical basis. The thing is, I mean, isotropy should be understood from a maths perspective. Like, why does it occur? I mean, it's good to relate both. So, but the thing is, in the course, this has not been discussed here.
Okay.
Why it comes here? The thing, but we need to know isotropy because isotropy is the simplest and it can be explained I mean, in a very mathematically rigorous fashion. Or maybe we can just discuss it, try to avoid to keep for other day, right?
Yeah.
Otherwise, it's like reading definitions is one thing. Let me put. I had some very good collection on quantum mechanics books. I think it was in tech semester 2. It was a book by these notes on quantum mechanics. Process. Yeah, I'll just share this. Yeah, it's visible, right?
No, not yet.
Not yet. Not yet. Okay, it seems like it was not shared. How about now?
Yes. Oh, I know this.
Yeah, this is a very. This is
Yes, it's
not
big,
like a
big.
proper book,
Yes,
but
it's a lot
because
of chapters in vector analysis. First chapter, I know this book.
yeah,
It has
the thing is
solutions also.
he has covered everything. That's the good thing about
I
this
know
book.
this
It's like a one, like go to book for every problem that you have in quantum mechanics, unlike
Oh, that's
others, right?
nice.
So
But
we
I
come.
haven't read this. I couldn't read this. I mean, yeah.
See, I got introduced to this book once I was just searching, and I saw that
I
okay,
think.
it looks like
I think.
it looks like. Then I thought
No,
that
I
okay,
think.
yeah.
I think we all are like, maybe both are. I mean, like people who study like us, like that. Keep on looking for good books. Like, this is a good book. We know, okay, this is a good book. We can keep this.
Yeah,
It's like that. Yeah, it's
yeah.
nice.
And then what happened is, and I saw, okay, why does it seem that this what Krishna Garikipati is teaching like this?
Yeah.
The thing is because the authors of this book actually did a lot of literature survey.
Hmm?
That's how they came up with this notes on content mechanics. Like the book is itself titled as notes on content. So you don't need to refer any other book. Any other book is just to get a proper understanding, but this has everything in one place. So our goal was to understand the isotropic hyperelasticity, right? Okay, so
Yeah, exactly. You can see
actually
here.
this is the relation. Yeah, this is the relation.
But this is so. But that is like, okay.
If you use the polar decomposer,
Can you cross this cross mark?
this one, huh?
No. Here, this contents bookmarks.
Okay. So something like
Just
this.
remove
Yeah,
that. Yeah, now it's clear.
yeah.
I can zoom here actually. Sorry, I can zoom in my figure also. So it's okay.
Okay. Yeah. Isotropic. The thing is, this is the condition.
Okay. So what he's doing is, so if I see 5 times that one,
Actually, we need to, for this, right, we need to go to Nagdi's notes. No, there is no better place than Nagdi's notes. I'll just go back to Nagdi notes because this is more like a compilation of everything. To understand, you have to actually go back to those standard books. So the semester 2 Biomac. I hope I have the yeah, here it is, Nagdi's notes. He has, no one explains better than him in isotrope.
Okay.
It's opening. There he actually has
It's a
shown
very
white.
big college, dude. UCB is like number 1, number 2.
What?
UCB, University of California, Berkeley.
Yeah.
It is number 1 and number 2 college.
That's true, yeah. Actually, there was a time when there were all those big guys in one place, right?
Yes.
This was like everyone wanted to move to places where there were a lot of big people, but I don't think it's anymore the case.
Correct.
Like now it is distributed everywhere.
Yeah.
All are the same,
Internet.
or none of them are the same. It's just like that. You see, right?
Correct.
The way the faculty recruitment is taking place in different institutions, all AIML everywhere. So I just wonder, I mean, in mechanics as well. So here he had very nicely discussed about this thing. Spatial invariance, okay. Has he? I mean, it has been quite a day. Nagdi.
Imagine working with Nagdi.
Yeah. Nagdi was from Palestine, and to the best of my knowledge.
What? I have to see.
Let me see, actually. Let me
Nagdi.
see. I know about NiFi was a Palestinian. That you know about NiFi, right? Nonlinear dynamics, nonlinear solid mechanics.
No.
He was a nonlinear guy in every domain. I don't know what Nagdi.
Paul M. Nagdi.
Okay, Paul Mansur. So let's see where he was from. Okay, Tehran. He was from this one. Yeah, Tehran. Yeah.
Israel.
No, Iran.
Tehran is not. Oh, it's Tel Aviv. Okay.
Yeah.
But Iran is very big, man. They have like few universities which are very good. Sharif University, I think.
Sharif, Isfahan.
Sharif, yeah.
Sharif, Isfahan,
Sharif
Hamid
is
Kabir.
very big. Yeah,
it's the gold standard.
Sharif is like MIT, that's what I heard, yeah.
Yeah, it is. It's the finest. I don't think even any Indian institution can be of that standard.
Correct. Like my friend told me that many people from Sharif, they'll do and they'll go to states.
Yeah, exactly. Yeah. Sharif. It's only after this. Okay, where is? I hope he has discussed, man, because it has been a long time looking at this book. Or maybe I'll just go to a third book that I have, is Nonlinear Solid Mechanics. Yeah, isotropically, yes. But we need nonlinear mechanics, right? Material symmetricity, what all is there? Derivation of superimposed linear energy, balance of energy. So supplements from the main text is 109. Let's see what they have to say. Okay, so this is one thing. Quadratic forms.
We will follow the lectures, no? I mean, it's okay, I think. Sure.
Okay, if you don't.
It's okay. I mean, lectures are also fine, yeah.
Okay, if otherwise the thing is, then I just have one go-to place book. This is Also fail.
Also fail. Okay.
Here it must be. The thing is, he has actually wrote it for nonlinear solid mechanics. So here everything is there. Yeah. Who's it talking? This Adobe Reader is very slow, man. I'm really tired. I don't know which is the better alternative.
Yeah, it is. Are you Windows? Okay, Windows is, I don't know, man. Windows is complicated.
Yeah, Windows only I'm using. The thing is, this laptop doesn't support Ubuntu. So what I'm doing is I'm using this Windows subsystem for Linux. So it gives Linux-like feeling. There is one software within it. It was jointly developed by what do you call by the by Microsoft and Canonical, both designed together. So it's like full support. Okay, where is page display enables scrolling? Yeah. So here he has done. This book I have read. I was just wondering that is it also there in the other book? Okay, you see, right now we come to, so there is this chapter. Damn. Okay, I'll just close the other so that it's not heavy. Okay, so you see, right, there is an hyperelastic materials, and there is one entire chapter on objectivity.
Okay. Some aspects of objectivity. Millions of elastic material response.
So you can only figure out how to use it.
Yeah, I mean, manual seems.
You check the menu?
Yeah,
Oh, yeah. Probably we should ask for the cable, right?
We're almost there. Hyperelasticity. Here he has actually described why should be the case. This book is actually very like this is a complete nonlinear book, nonlinear mechanics book. I mean, you can say that Nagdi is for starting purposes, but this is a complete book in itself. Like it can be understood. I mean, very rigorous, very detailed. So yeah, this hyperelastic.
March 10, no? March 10 is like.
Yeah.
That is solid book, man.
Yeah. Now you come here.
Sometime.
Of course, man. This actually today we'll just close this NPTEL discussions. Next from next week we'll. I mean, this Thursday onwards we'll just start. I mean, doing what we're planning to. Now you see here. Actually, this books really gives a good understanding. Now you see, even we can read everything here. So you see that we now restrict the strain energy function by a particular property that the material may possess, namely isotropy. This property is based on the physical idea that the response of the material when studied in a stress strain experiment is the same in all directions. One example of an approximately isotropic material with a wide range of applications is rubber. So rubber is the purely what you call it's almost what you call an ideal isotropic material, right? So in this section, we are concerned with the mathematical formulation of isotropy within the context of hyperelasticity. So now you see. So we consider an arbitrary point X of an elastic continuum body occupying the region omega naught. Okay, so this is the one. This it's the reference configuration at time t is equal to 0. So and it says that a motion xi may carry this point to a place x is equal to xi, which is just our mapping, specifying a location in the region omega, which is the current configuration. We now study the effect of rigid body motion superimposed on the reference configuration. Now you look, right? So we are superimposing on a reference configuration.
Yeah.
So that is the crux here. So we are imposing. So actually, that's why I said I think I'm making something wrong here. That we are not following. I was going in the wrong direction. So what we do is we now apply as I mean superimpose region on the reference. We postulate that a body occupying region omega naught is translated by the vector C and rotated by an orthogonal tensor Q. So now you are actually doing superimposed rigid body motion on the reference frame itself. So actually there should not be any pre-reference. Actually, it's some intermediate I should call it. It's like intermediate configuration. So we are first doing some intermediate configuration, which is given by x star is equal to C plus QX. OK, now and the arbitrary. So this is what we have. So this is before we had this mapping. But what we do is we are progressing step by step. First, we do some rigid body motion on the reference frame, take it to here, and then do our deformation. So this is all in virtual case. It's like you're doing in some virtual, like more of a virtual environment or thinking of it's like a thought experiment. And so we have, so this is the point. Now what you do is our aim is to, so our mapping will be xi star now. So we now demand that a different motion x is equal to xi star, capital X star, moves omega naught to the current configuration omega. So it's like we are doing some intermediate step, and then we need to define what will be the deformation which will lead to x star to the actual deformation. So this is the relation. So x is equal to xi is equal to xi star, and they take different arguments. So by chain rule, the deformation gradient will be defined as f is equal to partial x by capital X, and isn't it? And then we use chain rule. So it is like capital X by capital X star into capital X star by capital X. And what we saw from here, right? That capital X star with respect to capital X is just Q. I mean, the partial derivative of X star with respect to X is just Q, right? Because C is invariant. It's just a rigid, it's a constant. So only Q will remain. Yeah, exactly. Isn't it? When you take the partial derivative of X star with respect to this. So we put that and we saw that the deformation gradient will be F star Q. So it's like F star is which will lead us to the deformation, I mean, which will lead us to X with omega naught star to omega. And then we just do inverse on both sides with respect to Q. And then we say that, now we say that our hyperelastic material is isotropic relative to the reference configuration omega naught if the values of the strain energy psi f and psi f star are the same for all orthogonal tensors Q. You see, right? So even in this case and in this case, the energy should be the same.
Yes.
Okay, so this is for this and both the energy should be the same. And then that's what we call that. We can in others if we can show that.
Okay, so it's like you rotate the body.
Yeah, rotate the body with the same this one, right? So that it should not affect. So it's just like, again, let's look from the side that, I mean, from that perspective where we understand. It's just like your body is here and you see it like this. In the reference config, it does not change the work of this. I mean, the energy stored in this body. And so the strain, our stress and strain relationship won't change. I mean, it's from that side. Okay, we are looking from here that okay. So which means that the stress strain relationship in all directions will remain the same. So that is the subtle difference. In objectivity, it was the stress. I mean, whatever force you apply and the body, how the body reacts, should be independent of directions. I mean, every person should see the same phenomena happening. So that is the goal of what you call objectivity. Now you see, right? This objectivity doesn't hold for in relativistic mechanics, right?
Why not?
The reason is, if I see at time t and if the other person sees at time t, the thing is time difference doesn't remain the same. There is yeah, so it happens only for classical mechanics. It's assumed actually to be the same, or the thing is time difference is so less that it's equal to 0. When you talk about objectivity, you take both into account. Time and space both should change, and the material response to a particular set of loading should still be the same. It has a much stricter condition, but the thing is, generally we don't. That only Nagdi has done. If you look at Nagde's notes, you will find that he has taken in rigid body motion, there are 2 different times. So observers are looking at the same phenomenon at 2 different times and from 2 different locations. So that is how you define this vertical isotropy, and this is the relation for isotropy, which is 6.23. In other words, what it says that if we can show that a motion of an elastic body superimposed on any particularly translated and or rotated reference surface leads to the same strain energy at time t, then the material is said to be isotropic. So this line is the important one. Motion of elastic superimposed leads to the same strain energy at time t, then the material is said to be isotropic. However, if the result changes in the sense that 6.23 is not satisfied, it's said to be anisotropic. And then it says that's why it's always said we always get confused in this one, right? So it's also mentioned here that it's important to mention that 6.23, which was the principle of objectivity, is fundamentally distinct from the requirement 6.7, which states that the strain energy must be objective with during rigid body motions that is independent of an observer. So the latter condition holds for all materials. It is a fundamental physical requirement and must be satisfied, while the condition of isotropic response holds only for some materials. So it is a material dependent requirement and may or may not be satisfied, namely for isotropic materials, which makes a crucial difference. So this was essentially this actually books makes understand why is it the case. And the rest are all maths. Actually. Now we can go to lecture number 23-24, where we discussed isotropy. We'll just look at the relations. We won't go further, just relations. So how you describe that? So if you already say that what you call the material frame should not depend. Sorry, the strain energy functions should not depend on the what you call the orientation of the body, right? So and the thing is, and what we call, we always present our stored energy function in terms of deformation gradient or gradient Lagrange tensor, which is F transpose F. So which was given by C. So C here, right? C is the F transpose F. So this is C. C is equal to F transpose. So we actually usually write in terms of C. So all the what you call hyperelastic energy function is always in terms of C, capital C.
Yeah. Yeah.
The thing, and C stays in the reference configuration. Because of that, what we say is when we actually talk about so the thing is, if you say make some, if you do some superimposed rigid body motion on the reference configuration itself. So for that, for the energy to still remain the same, there must for the energy strain energy to still remain the same, there must be some other quantity upon which there must be some special quantities over which using which the strain energy is defined. Now let's just go to a matrix. So when we take a look at matrix, no matter how we transform a matrix, right? The determinant always remains the same, right?
Correct. Correct.
So it's one invariant of a matrix. Why? Because determinant is related to product of eigenvalues. So it's just like when we talk about this, when we find all these principal values, right, of a Cauchy stress matrix, then we saw that the sum always remains the same. Sigma 1 plus sigma 2 plus sigma 3 is always constant, no matter how you deform it. So at one point, at any point, the sum of principal values is always the same. Because so it's always equal to the sum of all.
Also,
and there is one.
Eigenvalues are also same.
Yeah, eigenvalues also remain the same. And the product of eigenvalues also remain the same.
I think trace also then.
Yeah, so trace is related to sum, and determinant is related to the product of eigenvalues.
Oh, yeah.
So these are two.
Yes, yes.
These are two invariants of a matrix, and there is one more. That the what you call the sum of product of two eigenvalues taken at one time is also constant. So it's like sigma 1, sigma 2, and sigma 3. These are the eigenvalues. Then sigma 1 into sigma 2 plus sigma 2 into sigma 3 plus sigma 3 into sigma. That's also a constant. So you have 3 invariants of any matrix.
Okay.
Yeah, so that's how we have. So there are 3 invariants of any matrix. So the thing is, for isotropic material, we would like the strain energy function to be dependent on certain quantities of the deformation gradient tensor, or what we call as the Green-Lagrange tensor, which is independent of the nature of f. I mean, not nature of how f is, or how the Cauchy-Green, what you call strain. I mean, this Cauchy-Green tensor is. So the thing is, we need to express in certain invariants of that Cauchy-Green tensor, and that is the reason that we always want our for isotropic hyperelasticity, we always express in terms of invariants, because only invariants can have that all that property that is required as per hyperelasticity. I mean, of all this isotropic hyperelasticity. So it depends on first, second, and third invariant. Now here we have assumed that okay, it's an inhomogeneous material in general. That is why the stress, it also depends on the position. At every point it will be different. That's what it says. However, what we see is, it's, you see that first invariant, which is the trace, second invariant is trace of c square, and the third is determinant. So it will only depend on this, and this is actually the foundation for isotropic hyperelasticity. And you can easily find the second Euler-Kirchhoff tensor. So S is equal to 2 into partial psi by partial c is equal to partial psi by partial e. Now you recall, right? The work conjugate of S was what? It was E dot.
Yeah.
And that's why you see that the derivative of psi with respect to E gives us the second Euler-Kirchhoff. And the derivative of psi with respect to F will give us the first Euler-Kirchhoff. So that's how they are related. And then once we have a C and once we have S, we can easily get all the stress relation, all the other stress stress tensors, right? So that's how they have just derived it, everything, just shown everything, and then we have this general expression.
I think the lectures is just explaining all these equations, man.
Yeah, actually, the lecture did not aim at making us understand the nature. Actually, these tensor operations are I mean, this is not what is required. Actually, we need to know how it came.
Yeah.
Like, things quantum mechanics is essentially philosophy, right? If you read the book by Chadwick, he doesn't do too much maths. He actually gives us the fundamental understanding of every concept. It's a very short book, just 112 pages or so. And Chadwick was one of these what do you call pioneers of quantum mechanics, right?
Wow.
James Chadwick. Not that Chadwick. There is some P. Chadwick. Yeah. I had his book is called Quantum Mechanics. It was written long back, 50 years around 50 years or so. And it's like Nagdi was one of the later pioneers. Now you see, right? So we have S and F. So then we just obtain the expressions, and then it just goes on and on. So there are 2 different types of hyperelastic models. One is called as phenomenological models. So phenomenological models are when you obtain constitutive relation based on experimental observations. So herein comes all this Mooney-Rivlin model. This is widely used in what you call in structural mechanics. Then you have Ogden model. Ogden model is widely used in for modeling rubber and all. Fung model is usually used in biomechanics. Then you have Saint-Venant-Kirchhoff. You already know it's Saint-Venant-Kirchhoff is a nonlinear version of linear elastic model. And then you have Marlowe. Your model is also used in biomechanics. So these are phenomenological. Phenomenological means based on what you observe. Or models based, which were constructed or built using experimental data. And then, you first hypothesize and then verify using experiments. Then there are something known as mechanistic models. So mechanistic models are those models which are derived from the principles of statistical mechanics. So this new Hookean model Yeah, so new Hookean model, right? Okay, just 5%, I see.
I'll just turn off my video. It's okay. Yeah.
Sure. I'll also turn off here so that it's conserved from both sides. Yeah. So it's new Hookean model, right? It's actually you can actually derive it using principles of statistical mechanics. We start with random walk problem. So random walk problem is the most. This is I think one of the most fundamental problems in statistical mechanics, right? To just teach us, to give us a flavor, right? In that case, random walk problem is based on say how it is expressed is you have a drunkard who has drunk a lot and then he walks, isn't it?
There are 4 options where we will go.
Yeah. Yeah, which way will go? Yeah, and then you give equal probability on all sides. So based on that, new Hookean model is constructed, and then you have combined mechanism.
And they compute pi value, everything in that area of circle. They do everything with that.
Yeah, yeah, exactly. That is based on taking any particular value, yeah, and then you say that which model will you use when. So new Hookean Munir-Evelyn polynomial Ogden, and then we have this compressive new Hookean hyperelastic model in which we also have this just a modified version. I mean, this is like the compressible version of new Hookean model. New Hookean model is essentially just given by this much. So this can easily be derived from, not easily, I mean, can be derived from statistical mechanics. So this part was just to make it compressible in nature. Okay, and then what we have is then all this, then it's just working on that. There is nothing philosophical anymore. So yeah. So I think, yeah, with this, we are actually closing our from next lecture, we'll literally start with what we are doing. No longer all this.
You can stop recording because yeah.
Sure. Yeah, I'll just
yeah.
Okay, so let's meet it next.